All right, in this video, we're going to continue on with where we left off in the last video, which was the concept of a limiting reactant. So we talked about what that was, the idea that a limiting reactant is the reactant that runs out first, and it's what dictates how much product is produced. In this video, we're going to look at two simple examples of how we can model that limiting reactant, and then we'll just keep on doing more stoichiometry problems in the videos to come. So in this problem here, we have a pictorial view of a chemical reaction, and so we have 6 hydrogen molecules and 4 chlorine molecules shown above. The chlorine molecules are the green, the hydrogen molecules are the white. And then after the reaction takes place, this is what the beaker or whatever this product is in. So the description below says when hydrogen and chlorine are combined in non-stoichiometric amounts. What that means is we haven't necessarily given the quantity here that is exact. We've just kind of given a random quantity, 6 and 4. So keep that in mind. One of these reactants will limit the amount of HCl that can be produced. This illustration shows a reaction in which hydrogen is present in excess and chlorine is the limiting reactant. Okay, so the description says that, but if I were to just give you the picture and say, okay, which reactant is the limiting reactant? Well, notice you have some excess reactant left over amid the product that you created, right? And so what is the white molecules? Remember, that was the hydrogen molecules. And so hydrogen is in excess because there's some left over. So that would imply then that the chlorine molecules, the Cl2, that was the limiting reactant. Now, it doesn't ask you to do this, but I'm going to ask you, what would be the balanced chemical equation for this reaction? Remember, a balanced chemical equation is just showing you the lowest whole number ratio of these are the reactants that you need to create this product. So let's look at how we would do that for this particular problem. So first thing I tell students to do, simply just write out what you see, right? So look at this. I see that there are 6 hydrogen molecules reacting with 4 chlorine molecules. And what does that produce? Well, that produces this product here. It's 1 chlorine and 1 hydrogen. So that's my HCl. And how many do I have? 1, 2, 3, 4, 5, 6, 7, 8. That produces 8 HCl's. And then plus, look at you have leftover hydrogens, right? You have leftover 2 hydrogen molecules. Okay, so that's just simply writing what I see. But that doesn't necessarily reflect the lowest whole number ratio balanced chemical equation, right? Apparently, does it take 6 hydrogens to make 8 HCl's? No, it doesn't take 6 because you had 2 left over, right? So if you have 2 hydrogen molecules left over, it didn't take 6. It really only took 4. So we can simplify that by doing this. All right, so that's actually more accurate, right? I just simplified both sides by subtracting 2 hydrogen molecules. Now, this makes sense. For every 4 hydrogen molecules and 4 chlorine molecules, it will produce 8 hydrogen chloride molecules. And that makes sense because, look, everything's balanced. You have 8 hydrogens, and 8 chlorines, 8 chlorines. But we're not done yet because this is not reduced to the lowest whole number ratio. 4, 4, and 8 is not the lowest whole number ratio. We can reduce that further to H2 plus Cl2 yields 2 HCl. So that would be the chemical equation that's reduced. It's balanced, it's stoichiometrically accurate, and that would be the reaction that's actually taking place here. So that was kind of a little extra something for you. You're welcome. But the key thing here that I wanted you to see is that the hydrogen was the excess reactant and the chlorine was the limiting because that ran out. All right. If you recall from the last video, we were looking at the reaction of nitrogen gas and hydrogen gas. So let me actually write that chemical reaction up. We're gonna do it down here. Okay, so we had the nitrogen gas plus the hydrogen gas, and it was 3H2 and it was balanced. And that reacted to produce 2NH3. So we already wrote this equation in the previous video, but I want to write that down again. Okay, so in this problem, Now it's saying how many moles of ammonia can be produced, so my little question mark under there, if you are reacting 2 moles of nitrogen gas, so I'll write 2 moles here, with 4 moles of hydrogen gas. That look more like a 4. There we go. So in this example, now you actually have a specific amount of both, right? You don't have excess. You have a defined amount of both reactants, and you need to figure out how much product can be produced. Well, similar to the sandwich example that I gave in the previous video, you need to figure out which one of these reactants will run out first, which one's the limiting reactant, because that's the one that's going to dictate how much product is actually produced. So here's how we do it. You essentially have to do the steps of stoichiometry for both reactants separately, just like we did for the sandwiches. So with the sandwiches, remember we said, hey, if I used up all the bread, what's the maximum amount of sandwiches I can make? And if I used up all the cheese, what's the max I can create? In the same example here, if I used up all of the nitrogen, what's the amount of product I can create? And then I would ask, if I used up all the hydrogen, how much product can I create? Whichever one creates less, that's the limiting reactant, and that actually is the amount of product. So let's go ahead and do that. First of all, I'm going to ignore the 4 moles of hydrogen. Okay, ignore that. And I'm going to say, all right, if I use up all the nitrogen, how much ammonia can I produce? So first step, convert to moles. It's already in moles. So second step is take that number of moles and use your mole ratio to convert to what the problem's asking you about. I'm converting from nitrogen into ammonia. And once again, these numbers that I'm putting here come from the balanced chemical equation. So for every 1 mole of nitrogen, there's 2 moles of ammonia. If I use up all of the nitrogen, 2 times 2 is 4. 4 moles of ammonia is how much I can create if I were to use all the nitrogen. I'm going to do the exact same thing now, but this time for the 4 moles of hydrogen. All right, and so I set that up. For every 3 moles of hydrogen, 2 moles of ammonia will get produced. Okay, 4 times 2 is 8. 8 divided by 3, that's approximately what? 2.67 moles of ammonia. All right, so if I use up all the nitrogen, max amount I can create is 4 moles. If I use up all of the hydrogen, maximum I can create is 2.67. So, which is the limiting reactant? The limiting reactant is the hydrogen. And so this first quantity will actually not even happen. That's not a real thing. The amount of product, the number of moles of ammonia that you can produce is 2.67, right? And notice you wouldn't have been able to predict that just simply from the quantities 2 and 4, because a common mistake students make is they think, oh, okay, well, 2 moles of nitrogen, 4 moles of hydrogen. Oh, you have less nitrogen, so nitrogen is the limiting. Not necessarily, because remember, the mole ratios are different. So you have to actually do the stoichiometry to figure out which is the limiting reactant. So how many moles of hydrogen gas, or excuse me, how many moles of ammonia can be produced? We just solved that, 2.67 moles of ammonia. Now, there are some follow-up questions here. We're not going to actually do them in this video just because of time. But the follow-up questions say, how many molecules of ammonia are produced? Well, you already know how many moles of ammonia are produced, so now you would just have to go from moles to molecules, and that's using Avogadro's number. So actually, I said I wasn't going to walk through it, but I might as well since, I mentioned it already. So continuing down here, 2.67 moles of ammonia. This would be your third step of stoichiometry, convert to the desired unit. It wants you to represent it in molecules. And so for every 1 mole of anything, in this case NH3, it's going to contain 6.022 times 10 to the 23rd molecules. Okay, and so multiplying that, get my calculator out here, 2.67 times Avogadro's number. 3 significant figures is what my answer needs to be in, and so I end up calculating, what is that, 1.61 times 10 to the 24th molecules of ammonia, NH3. So that's not really a stoichiometry as much as it just is a mole conversion. And then it does have one more question, how many atoms of hydrogen? So it's just getting you more practice with those conversions that we did way back in topic 2. So I already know how many molecules of ammonia there are. And remember, for every one molecule of ammonia, NH3, look, there's 3 hydrogens for every molecule. So I would just take this number here, 1.61 times 10 to the 24th, multiply that by 3. That's how many hydrogen atoms. I've run out of space, otherwise I would show that to you, but that's just a review there. All right, in the next video, we're going to look at another example of stoichiometry, brand new problem, so I will see you on the other side.